All right, so as a warm-up, let's go to compute the area between negative 1.96 and positive 1.96 for a normal distribution with mean of 0 and standard deviation of 1. That is, that's the normal distribution for z-scores. So choose normal CDF, and I would go from negative 1.96 to positive 1.96. 0, 1 already set here. Enter, and then enter again, and you see I get 0.95000. So basically about 95%. So the normal CDF from negative 1.96 to 1.96, mean of 0, standard deviation of 1, that's almost exactly 95%. So essentially, 95% of a normal distribution is between negative 1.96 and 1.96. So as you saw in the last example, approximately 95% of all values in a normal distribution will be within 1.96 standard deviations from the mean, either below or above. Okay, let's take a different one. Suppose x is a mean of 100 and standard deviation of 16. So we want to let's get a range of values. So approximately 95% of all values will be between which two numbers? Well, if you recall the last example, 95% of all values are within 1.96 standard deviations of the mean. So we need to find the values that are 1.96 standard deviations below and 1.96 standard deviations above the mean. So 100 minus 1.96 times 16 is 68.64. The mean of 100 plus 1.96 times the standard deviation of 16 is 131.64. So in this case, we can say, if assuming they were dealing with a normal distribution, 95% of all values will be between 68.64 and 131.64. Okay. In general, when the sampling distribution of a point estimate can reasonably be modeled as normal, the point estimate we observe will always be within 1.96 standard errors of the true value of interest about 95% of the time. So thus, a 95% confidence interval for the point estimate can be constructed using whatever the point estimate is, plus or minus 1.96 times the standard error. So we can be what's called 95% confident that this interval will capture the true value. Okay. Now, in order for this to work, in order to be accurate, there are certain conditions you need to check. So the normal approximation is crucial to the precision of this confidence interval. To ensure this, we should check the following conditions: that the sample observations are independent, and the sample size is large enough. So independence, that's usually the more difficult condition to check, usually. But for us, we'll just leave it at this, that if your sample is random, we'll assume independence. So if we take random samples from less than 10% of the population, so we have random selection, or if we randomly divide individuals into treatment and control groups, it's random assignment. If we have either of those, we can assume independence. The key word for this is that our sample is random. All right. The point estimate for the opportunity cost study was that 20% fewer students would buy a DVD if they were reminded that money not spent now could be spent later on something else. So the point estimate for this study can reasonably be modeled with a normal distribution, as we saw with the last lesson. And a proper standard error for this point estimate is 0.078. So a 95% confidence interval, we're going to assume the conditions have been met. It was a random sample, and normality can be assumed for this one. But just to summarize here, the point estimate is 0.2. The standard error given to you is 0.078. So if you want to do a 95% confidence interval, we got to figure out 0.2 minus 1.96 times 0.078. So 0.2 minus 1.96 times 0.078. And you see we get 0.04712. So about 4.7%. If I want to do the plus, let's just give my previous answer. Scroll back. And I put a plus there. Okay. Now the plus version is about 35%. So we are 95% confident that students given the reminder were between 4.7% and 35.3% less likely to buy the DVD. For one more example, back at the very beginning of our textbook, there is an experiment that was described that examined whether implanting a stent in the brain of a patient at risk for a stroke helps reduce the risk of stroke. So the results from the first 30 days of the study included 451 patients and are summarized here, where those in the treatment group were 33 out of 224 end up with a stroke, and the control group was only 13 out of 227. So actually, those that were in the treatment group were actually more of a risk. So the point estimate here, difference between the treatment and control groups. Treatment group is 33 out of 224. Control group is 13 out of 227. That comes out to be a difference of about 9%. So considering that the stent here, consider the stent we're studying the results. The conditions necessary to ensure that the point estimate of 0.09 may be assumed to come from the normal distribution. So we'll go ahead and assume it's normal. And let's also assume the standard error is 0.028. So let's construct a 95% confidence interval for the change in the 30-day stroke rates between the treatment and control groups. So point estimate is 0.09, standard error is 0.028. I go 0.09 minus 1.96 times 0.028. You get about 3.5%. If I add, I get about 14.49%. So we are 95% confident that patients receiving the stent were between 3.5% to 14.5% more likely to have a stroke. So this was not a good medical, this was not a medical procedure that helped.